Okay, hello. My name's Kyle from MASA, and today I'm going to be showing you how to make a point-of-load buck converter. Today we're going to be using this buck converter. It's the AP64351SP, and we're going to be designing this in the MASA-Dearborn Altium 365 workspace. First time I'm using it, so we'll see how it goes. All right, I recorded this video once already, and here's what I got. So I figured I'd just show you this as a little sneak peek of what's to come. But for now, I am going to not delete all of this. Um, I think I'll just make it again. All right, so right here we have the component selector. So we're going to go to all, and we're going to type in AP6 right here. So now we have a buck converter. And what we're going to do is we're going to go to the data sheet. Here is the data sheet. This is the point of load buck converter. Basically what it includes, it has built-in spread spectrum, which is great. Input voltage, a wide range of it, 3.8 volts to 40 volts. So we're going to be using 11.1 volts, and that's with a 3S2P battery. 3.5 amps output current, which is plenty because these are point of load buck converters, so only going to be supplying one board, and none of our boards really draw that much current. 570 kilohertz switching. Good efficiency, not the best efficiency, but as you can see here, it's in the 90s range with sufficient load for most output voltages. And yeah, I think it's just a good simple buck converter, and we're going to be potentially using this for our point of load converters on some of our boards. So to start with, we have this table. This is a really nice table. Basically, it just gives output voltages and it gives component values for these output voltages. So as you can see, we have 1.8 volts, 3.3 volts, and 5 volts, which are the three voltage levels we're going to be using on our boards. So that makes design a lot easier in our case. There's also a soft start on this, and we're just going to be copying the typical applications circuit for this one. So 10 nanofarads for the soft start. Then that equates to 3.7 times, uh, or yeah, 10 nanofarads divided by 3.7 is going to give time in milliseconds. I don't really know what it is off the top of my head, but yeah, let's just go for it. So we're going to go here, and what we're going to need to do, first of all, is we're going to tie VIN and enable together. Then we are going to get, not miscellaneous connectors, we're going to get a capacitor from devices, and we're going to put that on our VIN line. There's going to be 10 microfarads. This is just based on the data sheet. 10 microfarads. And we're going to draw a wire from here to here. All right, simple so far. Then we're going to put a ground label here, and we're going to put a power port at the top here. So this is our input voltage, right? And we mentioned that it was 11.1 volts. So there you go, 11.1 volts. Now we have to deal with this. So just to start off with, I'm just going to put a ground label right here. That won't get in the way at all. And then we are going to put something for our soft start. So we're just going to go back to capacitors. If you remember, the soft start capacitor was 10 nanofarads on the typical applications circuit. So we're just going to copy that. And then we're going to put a ground label underneath it. Okay, so it was really fast, sorry, but that's basically just the input side of things in the soft start as well. I'm going to show you this again. So as you can see, we tied V in to enable. We have input voltage right here. That goes to ground from capacitor. It's input filtering. And then we have the soft start capacitor. We also hooked up the ground to ground. So now we're going to head to this side. We're going to go to the output side first. So as you can see, from the bootstrapping pin to the switching pin, there's a capacitor, 100 nanofarads. Let's do that. 100 nanofarads. All right. Oopsie daisy. Let's not have that do that. And then we're going to get an inductor. As with all buck converters, you need to have an inductor on the output, unless it's built in, but those ones usually suck. Here we go. The inductor value they gave for the 5-volt buck converter was 5.5 microhenries. And then let's look back at the typical application schematic. So they have this open circuit right here. They represent it as a capacitor, but basically it's just a no-place component. We're not going to deal with that, so we're just ignoring it for now. And then they have the voltage divider that goes into the feedback for the microcontroller. So you have this little loop going on, a feedback loop. So let's just do that. We have two resistors, res 1, put it right on the output of that inductor, making things compact. Connect the two and feed that right back in to the feedback pin. Great. We're going to put a ground label underneath, and then we have to set the values. This one was 115K, and this one was 22.1K. Awesome. All right, so now on the output, we need to add some bulk capacitance, as with all buck converters, really. I don't think they ever build in bulk capacitance. I've never seen that. Sounds like a bad idea. Here you go. Put them in parallel, which adds the capacitance together. And they have two 22 microfarad capacitors on the output for a total of 44 microfarads. 22 microfarads. Perfect. So then we have wire connecting the two and another wire right here. We're going to grab another port, ground for now. Just ground these capacitors. And now let's grab a power port. I'm just going to set this as 5 volts. And now we have to deal with the compensation. Okay, so compensation pin, it needs a snubber on it and then a capacitor in parallel with that snubber. So what we're going to do is we're just going to grab one resistor, two capacitors. Put that right there and another cap right there. And then we're going to look up res 1. We're going to grab some wires there and there. And some ground labels, 1 and 2. This is 39 picofarads. This is 3.3 nanofarads. And this is 14 kiloohms. And just so I'm not confusing anybody, this is all specified in the typical application schematic. As you can see, this is for 5 volts, an output voltage of 5 volts. So I just copied the output capacitance, voltage divider there, the inductor, that bootstrap capacitor, and this compensation loop. Then we have 10 nanofarads for the soft start, 10 microfarads for the input filtering. So yeah, that's all there is to it. It's really simple, and it's just the exact same as what I have up there, except I did it a little bit differently that time. So for now, I'm going to show you how you annotate it. So you go to annotation, you go to annotate schematics, you update changes list, and then what you're going to want to do is you're going to want to go to accept changes, validate changes, and right here it shows affected objects. So it's just showing that it's adding designators to all these, and then you execute changes. So now if we go back and ignore that error, close that, you'll see that all of these have a label for them, which just makes things a lot easier to keep track of. So now that I've showed you kind of how you go about designing one of these things, just where everything is, as well as how to read the datasheet, a lot of the times you're going to have a harder time than this because this datasheet's very nice, given that it gives you this table as well as the typical application schematic. Sometimes you're going to have to read equations like this. Like as you can see, this is for the voltage divider for the feedback pin. And then you have the equation for the soft start time, inductor equation. So you have V out, which you know, V in, which you know, V out, which you know, frequency switching, which you know, delta IL, It's the inductor current ripple, and you have Vn again. For the inductor current ripple, I think that's just the acceptable ripple current that you can deal with. Uh, and so you'll just figure that out based on your specifications. Inductor peak current is calculated uh, by the load plus 1/2 the inductor current, or inductor ripple current. For the input capacitor, there's no equations, I guess. You can just read that and figure out what it says. Output capacitor, you have to figure out what your acceptable output voltage ripple is, and then use this equation. And then the bootstrap capacitor as well, there's no equation for it. The external loop compensation, this math is kind of annoying, so I'm glad that I don't have to do it. That's part of the reason why I picked this buck converter, so I wouldn't have to do it. But yeah, you can deal with that if you're not given a table like I am in my design. And yeah, that's basically all there is to it. So now I'm going to delete this, and I'm going to show you what I've done up there. So in this one, which is what I'm going to use for the real thing, as you can see when I click on this, I have a link to a part on DigiKey. So basically what I did in the previous one, which the audio didn't get recorded, just look for like an 0805 or a 1210 capacitor, 1206, something like that. And you're going to want like plus or minus 10% tolerance. Let's just look at the actual capacitor really quick, might as well. Okay, so you're going to want to look for something like this, plus or minus 20%. You want to make sure the voltage rating for the input capacitor is a lot higher than 11.1 volts, or else you're going to start derating your capacitance. So 25 volts is about twice as much. You're going to get a little bit of derating, but not much. For the temperature coefficient, this pretty much applies to all of them. You're going to want to look for like X5R, X7R. Those are usually pretty good. And for the operating temperature, typically you want something a bit higher than this, but this is fine, 55C to 85C, since we're going to be flying this in the desert. You're always going to want to do surface mount and package case for larger capacitance values, like 10 microfarads to 22 microfarads. That's kind of the larger capacitors in this design. You're either going to want 0805 or 1210 or like 1206. And that's basically all there is to it. For the voltage rating, for any component, you're usually going to want at least like twice as much as what you have on that line. So since this is like an 11.1 volt line, you're going to want to look for 25 or higher, 50 if you can, 100 if you can. So that's kind of what's going on with this capacitor. For this one, you don't have to worry about well, yeah, for this one, you're going to want to look for something a lot smaller, like 0402. If you can solder 0201, go for 0201, but you probably can't. So yeah, it's just 10 nanofarad cap, 0402 probably. You're going to want decent tolerance for this because it's determining soft start, but it's really not that important. Tolerance plus or minus 20 is probably fine. This is just like a general purpose 100 nanofarad cap, just find one like 0603, 0402, plus or minus 10, 20%. X5R and X7R as always for all of them. For this 14K resistor, all of these components, you're going to want these to be relatively, you want the small tolerances on these three because these are for the compensation loop, which is pretty important. So you're going to want to look for 39 picofarad. Like you can find, for these ones, I'm pretty sure I found, yeah, for capacitors it's a bit harder. Just go for like plus or minus 5% if you can find it, or plus or minus 10%, which is ideal. If you need to do plus or minus 20%, that's fine for these three components. Voltage divider, you want these to be relatively precise, so try for 1% if you can, 5% if you're on like a money crunch or something, but you probably won't be. For 22 microfarad caps, these are bulk capacitors. We're going to be using ceramic caps because that's perfectly reasonable to find in a ceramic case. But if you need more bulk capacitance for like a different buck converter, you'd probably go with aluminum electrolytic because you can find much higher capacitance values with those, and then maybe even tantalum capacitors, but usually you don't use those because of the high ESR. Same with aluminum. They have high ESR as well. Ceramic capacitors have low ESR. And also you want low ESL capacitors if you can. And then the inductor. What you're going to be looking out for with the inductor is current saturation. And also you want to make sure it's as small as possible, right? So on this buck converter, our current output is 3.5 amps. You're going to want to look for something there a little bit higher. And then also, uh, sometimes you won't be able to find the exact inductance value you want. You can you have a lot of wiggle room with the inductance. So you can go anywhere from like 5 to 6 microhenries and still be fine. Of course, it's not going to be completely accurate if you go for a different inductor value, but I think 5.6 microhenries is a standard inductance value. And so if you get a 5.6 microhenry inductor, I think you'll be golden for this design. So yeah, basically just look out for output current saturation, uh, the inductance value itself, and then the package size. Also, try to look for low DC resistance inductors. Okay, so that's basically all I have for you. That was just kind of a walkthrough on how you're going to read the data sheet. For the most part, copy the design, or if you need to go in and use the equations, you can go ahead and do that now that you know where to look for it. I also tried to walk you through the thinking process for picking out components, and there you go. This is how you design a point-of-load buck converter in the MASA-Dearborn Altium 365 workspace. And yeah.